Hey everyone, welcome back to BugNoJutsu. In today's video, we're diving into a very tricky but extremely interesting problem from LeetCode. Find the kth character in string game 2. At first glance, this problem may look impossible because it involves string operations that can potentially produce strings longer than the size of the universe. Literally. But don't worry. Today I'm going to explain it step by step, starting from a deep understanding of the problem, solving examples together, and finally walking you through a clever, optimized approach that can solve it without storing the actual string at all. So buckle up. This is going to be fun and packed with valuable algorithmic insights. Here's the problem in detail. Alice and Bob are playing a string game. Alice starts with a simple string consisting of a single letter A. Bob gives her a list of operations. There are only two types of operations. If the operation is 0, Alice appends the string to itself. Basically, she doubles the string by appending its copy. If the operation is 1, Alice shifts every character in the string to the next character in the English alphabet. For example, A becomes B, Z becomes A. Then, she appends this shifted string to the original string. The string keeps growing exponentially after every operation. Now here's the catch. We're given an integer k, and we need to find out what character is present at the kth position of the string after performing all the operations. But here's the tricky part. The number of operations can go up to 100, and after that many operations, the string length could become unimaginably large, far beyond anything we can store or even process directly in memory. The problem also guarantees that the string will have at least k characters after performing all operations. Our task: return the character at position k, without ever building the full string. Sounds impossible? Not quite. Let's solve it together. Let's walk through a sample example together, explaining how we'll approach this problem. Example: suppose we have k equals 10, operations equals 0, 1, 0, 1. Step-by-step forward simulation. Start with A. First operation is 0. Duplicate the string A becomes AA. Second operation is 1 shift AABB. Append AA plus BB AABB. Third operation is 0. Duplicate AABB plus AABB a BAABB. Fourth operation is 1. Shift AABB AABB BBCC BBCC. Append AABB AABB plus BBCC BBCC final string. But here's the thing, even in this small example the string has grown to 16 characters. Imagine this happening 100 times. It's impossible to simulate this forwardly for large inputs. Smart approach: reverse simulation. Now comes the clever idea. The string doubles at every step. So after all operations we know exactly how long the string is. We can simply compute length equals 2 power number underscore operations. We then trace back the kth character through the operations in reverse. Here's the logic. At every step we check which half of the string the kth character belongs to. If it's in the first half, no change needed. If it's in the second half, we subtract half the length to map it back to the first half. And if the operation was a shift operation, we record that shift. We keep doing this until we're back to the initial string A. Finally, we apply the total shift we recorded to A to get the result. This works because the string behaves predictably. First half always comes from previous string. Second half is either copied or shifted version. Let's understand what the code does, without reading code line by line. First, we compute the total length of the string after all operations. Since every operation doubles the length, we can compute this as 2 power length of operations. We initialize a shift counter to 0. Then we process the operations in reverse order. At each step, we find half the current length. If the kth character is in the second half, we map it back to the first half by subtracting the half length. If the operation was a shift, we increase the shift counter. We then have the length to go back one step. Finally, after all operations, we apply the total shift to the character, A, to get the result. The shift wraps around after Z. That's why we use modulo 26. This approach never stores the actual string. It only keeps tracking the position and shift count, which makes it extremely efficient. Now let's quickly discuss the time and space complexity. Time complexity. We process each operation exactly once in reverse order. Thus, time complexity is O number of operations, which is at most 100, so it's extremely fast. Space complexity. We only use a few integer variables like length, k, and shift. We do not build the string or store large data structures. Thus, the space complexity is 0.1. Constant space. This solution works even for the largest inputs within constraints. This problem teaches several important lessons. Simulation isn't always about building things forward. Sometimes, tracing backwards is far more efficient. Always look for predictable patterns in problems involving string duplication or operations on both halves. Don't fear large numbers. If growth is exponential but predictable, you can often solve it with clever math instead of brute force. This reverse simulation technique is quite powerful and applies to many advanced string problems and compression algorithms. That's it for today's deep dive. If you enjoyed this video, make sure to drop a like to support the channel. Subscribe if you love coding, algorithms, and anime-themed coding content. Comment below if you'd like me to cover more problems like this, or if you have any specific requests. Also, feel free to share your thoughts and solutions in the comments. I love reading through your approaches. Thanks for watching. See you in the next video.